Imagine walking into the office on a Monday morning. You grab your coffee, you open your laptop, and absolutely nothing loads.
Oh, yeah, the absolute worst case scenario.
Right. I mean, a multi-million-dollar business is just entirely paralyzed. Phones are dead, emails are stuck in the outbox, servers are unreachable. And the crazy part is, the culprit isn't like a massive, sophisticated cyber attack.
No, usually it's just a single missing digit in a gateway address somewhere.
Exactly. So today we're taking a deep dive into the invisible architecture that keeps our daily lives functioning. Because to most people, it really just feels like magic.
It does, but, to a network administrator, it isn't magic at all. It is a highly structured, deliberately engineered environment. It follows these really uncompromising rules.
And that is exactly our mission for today. We have this fascinating presentation slide deck called Module 17, Build a Small Network. And it's essentially a masterclass in designing, deploying, verifying, and troubleshooting a small business network.
And I mean, small is doing a lot of heavy lifting in that title.
Oh, absolutely. Even a quote-unquote small network still requires routers, switches, access points, servers, and all these endpoints communicating flawlessly thousands of times a second.
Yeah, it's incredibly complex.
So we're going to unpack the exact mental models and the diagnostic toolkits that network professionals use to build this stuff. And, more importantly, how they figure out what to do when it suddenly breaks.
Right. And I think we really have to start at the foundation here, because before you can even think about troubleshooting a network, you have to build it correctly in the first place.
Designing with purpose.
Exactly. The very first decision an administrator makes is device selection. They have to choose the routers and switches that will act as the traffic cops of your network.
So they're balancing like cost and speed.
Cost, speed, the types of ports, the operating system features, and a really critical factor, expandability.
Yeah, that expandability aspect is so crucial for a business because the industry draws this really hard line between fixed configuration devices and modular devices.
Yeah,
right?
that's right. With fixed hardware, what you see is basically what you get.
Like the ports are just soldered in. You literally can't add more.
Yeah. But modular devices, they actually have these physical expansion slots built into them. And what's fascinating here is why that matters so much for small businesses.
Because they grow.
Exactly. They grow. If you buy a fixed switch and you suddenly hire, say, 20 new people, well, you're out of luck. You basically have to rip out that switch, throw it in a closet, and buy a completely new, much more expensive one.
Ouch. That's a rough budget meeting.
Right. But modular devices allow the network to evolve dynamically. You can just, slide a new high-speed uplink module right into an empty slot.
Oh, nice.
Yeah, it prevents you from requiring a complete hardware replacement every 2 years. It's really about preserving that initial investment.
Okay, so you've future-proofed the hardware. You've built the physical roads. But physical roads are pretty useless if people don't actually know where the buildings are.
Right, you need a map.
Exactly, you need a map. And that brings us to IP addressing schemes. Network engineers use these incredibly strict, deliberately planned ways to assign IP addresses based on the device type.
They do. It's highly organized.
Like the default gateway, the router always gets an address, like 192.168.something.1 from a tiny /30 subnet.
Well, let's clarify what that /30 means for anyone who might be unfamiliar.
Oh, yeah, good call.
It's essentially network shorthand for a really tiny lockdown block of just 2 usable IP addresses. It's mathematically restricted.
Just 2, wow.
Yeah, just 2. You use it for a point-to-point connection between 2 routers. That ensures that no rogue device can easily just jump onto that specific segment of the network.
It makes a lot of sense. And then, like the wired desktop computers, they get a larger /26 subnet, which gives you about 60 usable addresses, while the servers might get a /29, which is, I think, 6 addresses.
Right.
I was thinking about this. And it's basically like zoning a city. If you build a city without a zoning plan, people just build whatever, wherever. And eventually, you get a noisy, polluting factory built right next to a quiet public library.
Yeah, that's a great analogy.
Right. The traffic just becomes a nightmare and everything breaks down.
And to take your city zoning analogy a step further, allocating these assignable ranges on strict subnet boundaries, it actually solves a massive administrative headache.
How so?
Well, imagine managing a security policy for a company. You really don't want to write 50 individual rules for 50 different computers just so they can access a database.
No, that sounds awful.
Right. So by zoning all 50 computers into one summarizing subnet block, you just write one single security rule for the entire block.
Oh, wow. So if you plug in a new computer tomorrow within that zone, it just automatically inherits all the security rules.
Exactly. It's incredibly efficient.
You zone the district once, and any new buildings follow the law. But what happens if this perfectly zoned, beautifully modular router just randomly catches fire? Because, I mean, if a single router goes down, the whole office is going to be sitting around twiddling their thumbs.
Well, that is where the principle of redundancy comes in. Downtime is just incredibly expensive, even for, like, a 5-person office.
Oh, yeah. Time is money.
So you achieve redundancy by systematically eliminating any single points of failure. This means installing duplicate network links.
So basically backup cable.
Basically, yeah. If a cable connecting two switches is accidentally severed, a backup path just instantly takes over. You might even have redundant routers connecting to entirely different internet service providers.
Okay, but ensuring the traffic continues to flow isn't enough, right? You have to ensure the right traffic flows first, and this introduces QoS, or quality of service. Basically, the router acts like a bouncer at a club. It prioritizes voice over IP calls as high priority, so they hit the internet backbone first, while, standard emails are just medium priority, and instant messaging is relegated to best effort.
Yeah, and the core mechanism behind that is latency sensitivity.
Latency sensitivity.
Yeah, so a dropped packet in an email doesn't really matter. The email client just quietly requests the packet again a fraction of a second later, and you literally never notice.
All right, the email still shows up.
But a dropped packet in a live VoIP call, suddenly you sound like a glitching robot to your most important client.
Oh, yeah, we've all been on those calls.
Exactly. So QoS ensures that the time-sensitive data always gets the fast lane.
Okay, let's pivot a bit here. We've built the roads, we've zoned the city, established the emergency lanes, but knowing how to route traffic doesn't matter if we don't understand the vehicles on the road. Like, what is actually generating all this data?
Right, so now we're moving into the application layer. And it really helps to draw a distinct functional line here between network applications and application layer services.
Okay, break that down for us.
Sure. So network applications are the software programs that communicate directly over the network. They are fully network aware.
So like your web browser or your email client.
Exactly. And then the application layer services, those are the invisible background helpers.
Oh, so the user doesn't interact with them directly.
Right, but the programs rely on them to use network resources. Think of print spooling or background file transfers. They prep the data so the lower layers of the network can actually transmit it.
Got it. And all of this relies on a sort of fundamental tool set of protocols, right? Like HTTP and HTTPS format your web traffic, SMTP, POP3, and IM handle routing and delivering your emails.
Yep. And DHCP dynamically hands out those IP addresses we zoned earlier, so you don't have to manually type them in.
Which is a lifesaver.
Yeah.
Oh, and DNS translates the human-friendly domain names into machine-readable IP addresses.
Exactly.
I do have a question, though, about how administrators interact with these protocols. Because there is a massive push in the industry right now to force everyone to use SSH, which is Secure Shell, instead of this older protocol called Telnet for remote administration.
Yes, a very strong push.
But if SSH and Telnet basically do the exact same thing, letting an admin log into a router from laptop across the building just to type commands, why force the switch?
It really comes down to the grim reality of packet sniffing.
Packet sniffing.
Yeah. Malicious actors can run software that passively copies the traffic flowing across a network. And Telnet, well, it was built in an era of implicit trust. It sends absolutely everything, including your administrator password, in plain text.
Wait, really? Yeah, just plain text.
Plain text. Sending a raw Telnet password across a modern network is basically like shouting your ATM PIN across a crowded room.
Oh, wow. So anyone listening can literally just write it down.
Exactly. But SSH uses really strong cryptographic algorithms to encrypt the entire session. So even if a hacker intercepts the traffic, all they see is just mathematical gibberish. It protects your credentials, your data, and honestly, it's just the only responsible way to remotely manage infrastructure today.
Okay, that makes total sense. So our secure, intelligently zoned, QoS prioritized network is just humming along perfectly.
Sounds beautiful.
Right. But then the business is wildly successful. They hire 50 new people. And we hit the growing pains phase. How do you actually scale this up without the whole thing just collapsing under its own weight.
Well, you cannot scale by guessing. You have to take a methodical approach, and it's built on 4 main pillars.
Okay, what are they?
First, you can't budget for new equipment if you don't have a detailed inventory of your current gear.
Right.
And you can't track your inventory if you don't have updated physical and logical documentation of where everything is actually plugged in.
Makes sense.
And finally, you won't know which gear is failing to keep up without rigorous traffic analysis.
And the traffic analysis part is where the visibility tools come into play, right?
Yeah.
I know network engineers use protocol analyzers like Wireshark. It literally peels back the invisible layer of the network.
Yes, Wireshark is indispensable.
You can just watch the packets fly by and see,
Yeah.
like, oh, 80% of our congestion is coming from this one single server streaming video.
Exactly. And even on just a single workstation, engineers will check the built-in Windows data usage tool or the task manager just to see which specific non-network app is suddenly hogging all the memory.
Because visibility is power.
It is. You cannot manage what you cannot measure. And this leads us to one of the most critical yet frequently ignored practices in IT establishing a network baseline.
Now, I have to push back here a little bit.
Oh, okay.
Capturing a baseline, running ping tests and trace routes, time-stamping them, archiving them in a folder when nothing is actually broken, isn't that just creating a mountain of extra paperwork for an already exhausted IT person?
I get why it looks like that.
Right, like why not just wait until a user complains the internet is slow and then look at the metrics?
Well, this highlights the huge difference between proactive and reactive management. Without a baseline, the whole concept of normal just doesn't exist.
What do you mean?
Let's say a user calls and complains that the database is slow. You test the connection, and a ping takes 50 milliseconds. Is the network struggling? Or has it always taken 50 milliseconds to reach that specific server just because of its physical distance?
Okay, yeah. You have literally no idea if that 50 milliseconds is the symptom of a failing switch or just the baseline reality of that connection.
Exactly. But by archiving performance data over time, you can compare a Tuesday in August to a Tuesday in September.
Right?
If the average latency slowly creeps up from, say, 5 milliseconds to 15 milliseconds, you have mathematically identified a negative trend. You can find and replace a failing cable before it causes a total outage. The baseline eliminates the guesswork.
Okay. That is a very compelling argument for the paperwork. But, despite perfect scaling and baseline monitoring, reality happens.
It always does.
A backhoe cuts a fiber cable outside the building, a switch dies, someone unplugs the wrong cord in the server room, something will inevitably break.
Oh, absolutely.
Which brings us to the detective toolkit.
Yes, the verification and diagnostic commands. This is where the theoretical architecture meets cold, hard reality.
Let's get into it.
The most fundamental tool in that kit is the ping command. It tests layer 3 connectivity.
Which basically means it checks if the logical IP addresses can actually talk to each other? Really?
Exactly. It does this using ICMP, the Internet Control Message Protocol, which is essentially the diagnostic language of the Internet.
Oh.
It sends an echo request, and it just waits for an echo reply.
And there's a really quirky difference between operating systems here that I found fascinating.
Oh, yeah.
If you were on a standard Windows machine and you type ping, it sends exactly 4 ICMP echo requests and gives you this nice readable text block of the results.
Very user-friendly.
But if you're working directly inside a Cisco router using the iOS operating system, it defaults to 5 echoes. And it just spits out these single character indicators.
Right, but those single characters tell a very precise story to a trained eye.
Like what?
Well, an exclamation point means a successful receipt of an echo reply. Your layer 3 connectivity is fully validated.
Okay, good to see.
A period means the time expired waiting for a reply, which indicates a roadblock somewhere along the path. And a U means a router along the way actively rejected the packet and returned a destination unreachable message.
But ping only tells you if the connection is broken. It doesn't actually tell you where it's broken.
Correct.
Like if the server is 5 routers away, which router dropped the ball? For that, you need traceroute, right?
Exactly. Traceroute returns a sequential list of every single hop, every single router the packet takes on its way to the destination.
Yes, and there is a brilliant piece of engineering behind how traceroute actually works, especially on Cisco iOS and Linux systems.
It's very clever.
While Windows uses standard ICMP echo requests for its trace, iOS uses UDP packets with an intentionally invalid port number.
Yep.
Wait, I meant to ask about this. Why send a packet to an invalid port on purpose?
So that when the packet finally reaches the actual destination machine, that machine will say, hey, I don't have any service listening on this port, and it will return a specific ICMP port unreachable message.
Oh.
Yeah, that unique error message is how the tracing program knows it has finally reached the end of the line, rather than just hitting another intermediate router along the path.
That is incredibly clever. They literally weaponized an error message to confirm delivery.
They did, and engineers use local commands too. On a Windows machine, running ipconfig/all shows your IP, subnet mask, default gateway, and DNS.
And on Linux or macOS, it's ifconfig.
Right. And then there's checking the ARP cache with
Now,
ARP-K.
what does the ARP cache tell you?
The ARP cache is vital. It verifies that layer 2, which is the physical MAC address hard-coded into your network card, is successfully mapping to layer 3, your logical IP address.
So connecting the physical to the logical.
Exactly. If ARP fails, the data literally doesn't know which physical piece of silicon to travel to next. And on the networking gear itself, technicians rely heavily on show commands.
Like show IP interface brief.
Yeah, that gives a bird's eye view of every port and whether it is up or down. And show version verifies the device's uptime, configuration registers, and hardware details.
Okay, here's where it gets really interesting. Network engineers use a command called show CDP neighbors.
Yes, CDP.
CDP is the Cisco Discovery Protocol. It operates at the data link layer, meaning these devices can chat and learn about each other, even if the IP addresses are completely misconfigured.
It's a very powerful tool.
Right. It reveals device IDs, the platform model, and exactly which port they are plugged into. But network professionals actually view CDP as a massive security risk, don't they?
They do, because it's a double-edged sword. CDP is profoundly useful for an administrator trying to map out a tangled web of cables in a messy server room.
Sure.
But it happily hands that exact same roadmap to a hacker.
Right. Like if I walk into a corporate conference room and just plug my rogue laptop into an Ethernet wall jack, CDP might just broadcast the exact model of the switch I'm connected to, its operating system version, and its management address.
Yeah, actually, you have to disable this on user-facing ports using the no CDP enable command. Otherwise, hackers can just silently map your entire infrastructure from an empty office.
That is terrifying.
It is. But stepping back, look at all these tools. Ping, traceroute, ARP, show interfaces. These aren't just strings of text. They constitute a diagnostic surgical kit. They allow an administrator to mentally visualize an entirely invisible digital environment.
Which brings us to actually solving the crime. We have our surgical kit. But how do we apply it methodically? Because mashing buttons and guessing will just break things further.
Oh, absolutely.
The industry standard is a strict 6-step troubleshooting methodology based directly on the scientific method. So let's walk through a scenario. A user calls and says the internet is broken.
Okay, step 1 is identify the problem, which almost always means interrogating the user, because the internet is broken usually translates to, I can't reach this one specific intranet portal.
So true. And step 2 is establish a theory of probable causes. Based on the symptoms, maybe the DNS server just isn't resolving the name.
Right. Then step 3, test the theory to determine the exact cause. You can ping the server's IP address directly by passing DNS. If it replies, well, your theory is correct.
Perfect. Step 4 is establish a plan of action and implement it. So maybe you flush the DNS cache. Step 5 is verify the solution works and implement preventive measures. So you'd have the user load the page while you're still on the phone.
Exactly. And step 6, which everyone hates but is crucial, document your findings, actions, and outcomes for the next time this inevitably happens.
Documentation, the bane of IT.
Truly. But part of this methodology is also knowing when to stop and escalate.
What do you mean?
Well, not every problem can or should be resolved by a frontline technician. If step 3 reveals that a modular switchblade is physically fried and needs replacing, you must escalate.
Right, because buying new hardware requires manager approval and financial sign-off.
Exactly. Knowing the limits of your access level and authority is a core competency.
Speaking of limits, there is a very stern warning in network administration regarding a specific Cisco iOS command. Debug.
Oh, yes. Handle with care.
The debug ICMP command gives you real-time, play-by-play messages of everything happening on the router. But you have to be so incredibly careful.
You really do.
Because using the debug all command is like trying to troubleshoot a car engine by ripping off the hood while driving 80 miles an hour down the highway. The sheer volume of data will literally crash the router's CPU and take down the entire network you're trying to fix.
Yet you only ever debug highly specific processes, and as a practical quirk, if you are connected remotely via SSH, debug output doesn't even show up on your screen by default. Yeah, you have to explicitly type the terminal monitor command to force the router to redirect those log messages to your remote terminal session.
That's a great pro tip. So let's talk about the usual suspects, the common connectivity issues you actually find when using these 6 steps.
Okay.
The first one is a duplex mismatch. You have half duplex, where communication goes one direction at a time, and full duplex, where it flows both ways simultaneously.
Right, and Ethernet auto-negotiation is supposed to prevent this by ensuring both connected devices agree on the highest performance mode.
Supposed to.
Yes, but occasionally the negotiation just fails.
I always picture this as a traffic nightmare. Full duplex is a modern 2-lane highway cars flow both ways without stopping. Half duplex is one of those old 1-lane country bridges where only one side can cross at a time.
That's a good way to look at it.
Right. If the switch thinks it's a highway and the computer thinks it's a 1-lane bridge, they mix. And the crazy thing is, the data still flows. The link lights are green. But the performance just turns into a spectacular grinding traffic jam.
Which is exactly why mismatches are notoriously difficult to troubleshoot. A simple ping might look perfectly normal, but any large file transfer just crawls to a halt.
So frustrating.
Extremely. Another incredibly common issue revolves around IP addressing, specifically when a Windows machine self-assigns an address starting with 169.254.
Ah, the APA address. Automatic private IP addressing. Let's connect this to something we've probably all felt at some point. You sit down at your desk and you see that dreadful yellow exclamation mark over your Wi-Fi icon.
Yes, that yellow exclamation mark is very often tied to this exact phenomenon. The APA address is the ultimate telltale heart of network troubleshooting.
How so?
Well, when an IT person remotes into your machine, runs an ipconfig command, and sees 169.254, it instantly proves 2 things.
Okay, what's first?
First, the physical layer, the cable, or the Wi-Fi card works perfectly because the machine is actively shouting onto the network to request an address.
Right.
But second, it proves the DHCP server is completely unreachable and failing to hand out an address. It is an instant definitive diagnosis.
Oh, wow. Now, Linux and macOS handle it a bit differently, don't they? I think they usually just leave the IPv4 address blank if DHCP fails. But Windows raises that 2069.254 flag.
Yep, it's very recognizable.
The last major suspect is the default gateway. If that address is missing or typed incorrectly, your laptop can talk to other computers in the same office, but it is completely locked out of any remote networks or the internet. Your packets get to the edge of the local network and just drop off a cliff.
Because the default gateway is the closest router that knows how to forward traffic to the outside world. Network routing tables elegantly refer to it as the gateway of last resort.
The gateway of last resort.
Yeah. If the router doesn't know where a specific destination is, it hands it to the gateway of last resort and just hopes for the best.
It sounds like a sci-fi novel, but it's really just the blinking box in the closet.
Pretty much.
Bring this all together. Building a network is so much more than just plugging Ethernet cables into a plastic box. It is a living, breathing ecosystem.
Absolutely.
It demands deliberate architectural design, strict protocol management, proactive baseline monitoring, and, when things inevitably go dark, a methodical, scientific approach to troubleshooting.
It requires a technician to not just memorize what the hardware is doing, but to deeply understand why it is doing it and how to speak its underlying language to uncover the truth.
Which leaves me with a thought I really can't shake. We've spent this entire deep dive marveling at the manual, hands-on nature of all this.
Yeah, very hands-on.
A human being sitting at a terminal, running trace routes, checking ARP caches, hunting for a 169.254 address, or typing show version to check a router's uptime. But with the rapid rise of AI and machine learning, I just have to wonder, how far away are we from networks that are entirely self-aware?
That is a fascinating question.
Right, like networks that constantly run their own baselines in the background, instantly detect their own duplex mismatches, and dynamically reroute traffic around a failing switchblade before the human administrator even realizes there was a problem. Will the detective toolkit we just explored become a lost art?
It just might.
It's definitely something for you to mull over the next time you open your laptop and the internet just magically works. Thank you for joining us on this deep dive. Stay curious, and we'll catch you next time.